Hi everyone, welcome back. This is the second video on the series of control engineering, and today we're going to talk about integrator windup. So what exactly is integrator windup and how we can solve it? Okay, so when you design a controller for a system, there are some non-linear effects on every system that we have to take into consideration. So for example, this is max speed, max values. For example, if you have valves, they can only be so much, 100% open, 100% closed, and so on. So for example, you design a system and everything seems okay in the simulation, right? You have like the small overshoot and a nice rise time, nice settling time. But then in practice, you try it out, for example, in a motor, and then the control variable reaches the actuator limits, right? So what happens here is that the feedback loop is broken, and this error you have will continue to be integrated. So the integral term of the controller becomes very large, and this is known as a windup. So then you have this massive overshoot and a huge rise time and a huge settling time you're not planning for. So how does this look? Say, for example, you have a set point change. So you go from 0 to 1. Imagine this is a motor. So when you're not planning for this, the actuator is going to saturate. So it's going to jump up to the max value it can. What happens here is that the integral term is going to shoot up as well. And this will keep going, and this will keep the actuator saturated because the value of the error is still positive. And when we start to go down, we see the actuator desaturate, and then the integral goes up again, it saturates again. And this goes on until we can stabilize the error, right? So you have this huge set point change, the actuator saturates, and the integral term starts increasing. How can we fix this? So in the early days, we had set point limitations, which was basically limit your system to a certain value. But this can be not very useful or expensive or time consuming. Then incremental algorithms were created, which inhibits the integration factor. So if our integral shoots up a lot, this algorithm will reduce it and try to keep it at 0, so balanced. In modern day, this is called back calculation in digital control. And we can go through a few steps of how this works. So we have our output saturates, and we will try to recompute the integral part and give it back to the system, basically creating a new feedback loop. And this new response is going to be delayed by a time constant. So we can observe it here. Say we have a normal PID parallel controller, and then we have our derivative term or proportional term. And instead of our normal integral term, we're going to compare the output of the control system with the output of the actuator, and we'll create a new error signal which compares this. So if this value U is much bigger, then we have a positive error, or if it's smaller, we have a negative one, and this will be fed through the delay of the integrator, and this error system will go back into the system, and then the integral will be recalculated, and then we can try to bring it back to 0 again. So we have a stabilized system. This time constant we use for a delay has to be bigger than the derivative term, but smaller than the normal integral term, so we don't cause oversaturation or time problems. And a good rule of thumb is that this is the square root of time derivative times the integral time. So how would this look after we correct this error? So the anti-windup response, say again you have your set point. Now the system is not going to try to play catch up because it doesn't have a huge integral error to correct. As soon as the system saturates, it's a much smaller time until the integral corrects itself to 0 and our system desaturates and our set point is achieved. So we have no overshoot or really small overshoot depending on how much gain we add to this integral term. We have a saturation that resolves quickly and we stop our excessive integration. So this is basically how the windup works and what problems it causes and how to solve it with a little bit of error calculation. I hope this helped and it's explanatory. If you have any doubts, you can leave a comment, and thank you.